Okay, so thank you, Cosimo, for the introduction. Thank you, Brandon, Cosimo, and Sasha for inviting me to this very interesting workshop. I will present this afternoon some background results, I would say, on the classical control of flexible robots. And by this, I include the two classes of robot arms having concentrated elasticity at the joints for a number of reasons, or distributed along their links. I've heard very interesting modeling talk this morning, but please keep into account that you can, for control design, you may need a more simplified model in general. Okay, you may not have to go to the full dynamic modeling that you need for simulating or reproducing a real-world situation. So with this in mind, the summary of my talk will start, so I will start with a kind of categorization of the various type of soft robots that we are dealing with, just to fix, let's say, context, because this is very important. Then I will deal a lot with robot with flexible joint, which was my original PhD thesis, and I left this topic for a while, and then I'm recovering on that now, so the dynamic modeling. And I will consider first the problem of trajectory tracking, so following the desired reference trajectory in the configuration or in the Cartesian space, which is solved in this case by feedback linearization method, which is the extension of the version of computed torque for rigid robot arms. And then I will move to regulation. Usually these two control problems are considered in the reverse order because regulation is easier than trajectory tracking in general. But the reason why I organized this is because on regulation, so on using only a partial state feedback, we have learned this morning that measuring the state of soft manipulators is very complex. And because it deals also with the problem of handling gravity, which is per se a special problem. And also because this will let me introduce a different way, different than feedback linearization or just Lyapunov-based technique, to handle certain problems, which is this feedback equivalence concept is a very standard one, but I will present three applications of this concept, which were very successful indeed. And this again on flexible joint robot, although the same idea can be extended possibly also to soft manipulator of the continuous type. If we have time, I will show a couple of videos on application of these techniques for flexible joint robots. Otherwise, I will skip and move to the second part, which is dealing with flexible link robots, again, dynamic modeling. And as for flexible joint robot, I will point out some structural properties which are relevant for control, namely the role of the so-called zero dynamics. Zero dynamics, for those of you who have a background in linear control theory, is just the location of the zero of a transfer function in a linear single input, single output system, but it can be also generalized to the concept, this concept to the case of nonlinear systems, where you associate the dynamic when the output are fixed to be constant or zero. And then in that case, I will show some simple control schemes for regulation and for trajectory tracking at the joint level. And because of the nature of the zero dynamic in that particular case, I will show what are the criticalities in trying to execute trajectory at the end effector level of a flexible link arm. So what we would like to do, in fact, the tip of the end effector is what we are more concerned with. But in that case, because of the presence of an unstable zero dynamics, we need to invert the system in a very special way. And then finally, I will try to present things in such a way that some of this may be extended to the control of soft manipulator. I will limit myself to the planar case. In particular, I will use the so-called piecewise continuous curve dynamic model that also Cosimo uses or introduced probably. And just to highlight some very recent work that we are doing together with a master student of mine, Pietro Pustina. So classes of soft robot. Elastic joint robot are traditional industrial robot, in fact. In fact, elasticity at the joint was seen as a parasitic effect for rigid structure that are built in a massive way with stiff link because of end effector accuracy requirement. But indeed, nowadays, there are lightweight links still stiff, but they have typically compliant elements distributed in the structure, which arise either from the presence of elastic transmission, typically harmonic drives, or serial elastic actuation, or cable-driven robots. But you may also include some soft coverage of the link in order to absorb impact energy if these lightweight robots are being used in the presence of humans, so for physical human-robot interaction. Now, another aspect which is relevant of joint elasticity is that the elastic joints decouple what is still a large inertia of the motor with respect to the small inertia of a lightweight link. And this is very important to transfer the minimum amount of energy in an undesired impact with the environment or with a human. So this is a very important thing. Indeed, as we have learned for more general cases, this is the first case where sensing is very important because in order to understand the state of the robot, we need to have at least a measurement of the encoder on the motor side and of the position of the link, or a jointer sensor, or a combination of this. And this is because we need this information to get a full state picture and compensate for deflection in the static case or vibration while tracking trajectory. So the whole class of torque control robots nowadays, and here I'm listing a few of them, are in fact robots with elastic joint. They use the joint elasticity in order to be able to impose the commanded torque from the user. Now there's another class of, let's say, joint elastic things, in the sense that the actuator itself contains an elastic device, which are variable stiffness actuation. So typically, you have double the number of motors, either in a serial configuration or in an antagonistic-agonistic pair, and you are able to change the stiffness of the joint together with the motion of the links. So these are, again, flexible joint robot, but a characteristic in order to have a variable stiffness is that the flexibility, either by nonlinear spring or by nonlinear kinematics attached to linear spring, should include some nonlinear effect. Otherwise, you cannot change the stiffness. And there are several ways of using this. This is the traditional one introduced by Antonio Bicchi. So stiff when moving slow in order to have a performance, and becoming soft when getting fast in order to keep safety. There's a possibility of using in parallel the passive joint elasticity and some active impedance control strategy, so that you can amplify the possibility of compliance in the various task direction by combining this effect. And finally, there are many more things that can be done with variable stiffness actuation. First of all, these devices are more robust to impact. You can use optimally energy, and you can release energy in an impulsive way so that you achieve extremely dynamic performance. Now, the third class is robot with flexible link. So what is the difference is that we don't consider any more concentrated deflection or deformation. This is distributed along the length of the arm. Why? Because these arms are very long and they have a slender design, because the application is needed in space, underwater, under earth, and so on. At the same time, they are lightweight because you have to save weights, because this costs, especially in space application. There are other reasons why an apparently rigid link robot behaves as a flexible one, is when it's moving large payload or hitting with large forces the environment, or in general when you're increasing the speed up to the limit of the actuation. Now, again, modeling is important, because if you neglect model, then you will design if you neglect flexibility, like in the joint case, you will have a limitation in performance, both in static and in dynamic condition. So including the modeling in the control design is very important to achieve a superior performance. Now, in this case, a very important point, and you can fix the idea, look at the third picture in a row, which is the flexible arm, 3R flexible arm of the University of Tokyo. Now, if you focus on a motion of the end effector, you may wish to track a desired trajectory. Now, the first command that you give at the joint will typically be associated with an acceleration of the tip, which is in the opposite direction. So this is a rule of thumb to understanding that there's a non-minimum phase nature in the mapping between command at the joints and non-collocated output for the system. And I think that this problem is a problem that may happen also in the case of soft manipulator, continuum soft manipulator. So keep this in mind because I may say something later on. Now, the last class is continuum soft manipulator. I will very briefly say why this is important. Indeed, there are many useful special robotic applications that require this possibility of reconfiguring the arm. I would say that one main difference between flexible link robots and continuous soft manipulators is that you're able, by control, to keep deformed configuration as your target, while, as you know, a flexible arm, in the absence of gravity or in the absence of external contact, will resume always its undeformed configuration, no matter which controller you're using in a static situation. Well, this is not the case. And you can use this capability of soft manipulator to penetrate very cluttered environment, to embrace objects and things like that. The modeling, I understand there are many techniques, many of them include approximation. You can model only the kinematic aspect or the quasi-static aspect, or more recently also the dynamic aspect of your continuum soft manipulator. And let me conclude with this brief panorama with saying that at the same time, there are control issues for this class of robot, as far as I can see it, in the fact that there are a large number of degrees of freedom, so these devices are highly redundant with respect to the specific task that you want to achieve. If you don't want to control the configuration or the curvature along the whole structure, and you want just to position the tip of your flexible robot, I've seen this morning a very interesting simulation by Grazioso, I guess, then you have redundancy with respect to the given task. And you have to consider what happens to the extra degrees of freedom, which are not seen from the point of view of the task output. And on the other side, you have a classical situation of underactuation. Underactuation may be hidden between the construction or more explicit. For instance, I may consider the fact that you have a segmented structure. Each segment has, in principle, an individual actuation, but some of these actuators may fail or may not be present because of cost and construction. So in that case, you have an explicit underactuation that you have to deal with, and the same underactuation that you have for flexible link and elastic joint cases. The main difference is that you have here a distributed type of actuation. Now, with this in mind, let's focus on the modeling of robotic flexible joints. There are a number of assumptions that are made, which leads to the so-called reduced model of Spong, introduced in '87. This is not the most complete one, but it's the most used and also reasonable one. And as you can see, you end up with a 2n second order differential equation. These are ordinary differential equation. If you have n joints which are flexible and they are moving n rigid links, so you double the number of generalized coordinates, and you end up with what is called the link equation, which has a 0 on the right-hand side, which means that you don't have an explicit input on the coordinate, on the link coordinate, because you're applying torque on the motor side. And the second are the motor equation, which are very simple. But more than that, I would like to focus on a very simple example. Just say one elastic joints or a simple mass spring mass system, if you consider the linear case. Because this is in fact already in this simple linear case showing some structural properties. So here are the model. You have an input torque applied to a first mass, which has B, which may be the inertia of the motor, a spring connecting a link mass M, and you have a position theta of the motor, you have a position q for the link, and you have this elastic coupling between the two. The model is linear because we are assuming small deformation, and you can design a transfer function between the input torque, and if you want to control the position of the motor, which makes sense because this is typically what you measure in a conventional robot. So you have an encoder mounted on the motor side of the transmission. You have this type of transfer function, which has relative degree 2, so there are 2 zeros and 4 poles. It has a passive structure in the sense that you can tell this from the location of the zeros and the pole on the imaginary axis or in the Bode plot of the frequency response. And because of this, you can very easily achieve stabilization by doing an output feedback from the motor position. Whereas if you consider what is more interesting, the transfer function between the input torque and the position of the driven link, so beyond elasticity, then all of a sudden, the denominator is still the same because the dynamics of the system is still the same, the characteristics are the same, but the transfer function has no zeros. So you have a maximum relative degree, no 0 and 4 poles. So the difference is 4. And in fact, you can see, looking at, so you can eliminate one integrator and having a mapping between torques and velocities or of the motor of the link, and you have a transfer function of this kind. And you can recognize the typical anti-resonance resonance frequency behavior of the amplitude of the transfer function of elastic joint when the output is the motor position or velocity, while you have a pure resonance at the special frequency for the link output. So in the first case, you have zeros, and these zeros are minimum phase. In fact, you can see that the phase never goes below 90 degrees when the output is velocity, or never goes below minus 180 degrees when the output is in position, while you have a different situation in the case of a link output, because you have a pure resonance, you have no zeros at all. So this makes a lot of difference from the control point of view. Now let's go back to the full nonlinear model, and this is again the model, and not by chance, I mean, this is a standard result. If you take the link position as output, so those that have no zeros, in fact, in the linear case, but also in the nonlinear case, you can say that there's no zero dynamics associated to the fact that you're fixing the position output Q to a certain value, then this is a linearizing output, also called a flat output. So, which means that you can you can find a control. And in fact, you can find this control just by looking at the second order dynamics and differentiating twice the first equation, which is always equal to 0, until the acceleration of the motor appears, and then replacing the second equation and solving for tau. So by applying this very complex law, I would say, you are able to achieve a linear linear behavior and also input-output decoupled. So every new input UI for each joint control the fourth derivative of the associated joint variable or link variable. Indeed, you have to stabilize this, but you can do this with standard techniques in the linear domain, single input, single output. So this is a trivial aspect. Now, if you look at this control law, you see that you have a Q, you have Q dot, you have Q double dot, and even Q triple dot. So you need higher derivatives, which nobody would give you. But likely enough, if the model is good, from the model, all these quantities can be computed from standard measurement, which are, for instance, position of the motor, position of the link, or position of the motor and joint torque sensor, and numerically differentiating only once this quantity in order to get the full state. And from this full state, you can also derive the expression of Q double dot and Q triple dot. So you don't, this is implementable, and in fact has been implemented. On the other side, in the expression of the controller, you need also a higher order derivative of the dynamic model terms, which is kind of boring. In fact, if you write this for a 7 degrees of freedom arm, you will get lost. Likely enough, we developed also a Newton-Euler recursive method, which does not require to go into the symbolic part, but computes all the needed quantity for implementing feedback linearization for the elastic joint case by numerical transformation, and the complexity is ON3. Now, what is the difference between using a rigid model and so neglecting joint elasticity and having instead the full model? So this is an old video by Mark Spong, which shows that if you implement on a joint elastic prototype a controller, a feedback linearization controller, which neglects completely elasticity, you get a very tremendous behavior. While if you're implementing all these terms, and I'm putting in red the extra terms that you need, then the same motion can be achieved in a perfect way. Okay, you need to do model identification and so on, but at the same level of complexity, you have much better performance. So this motivates things for a simple prototype, but also in the industrial setting, if you have joint elasticity, because of the type of the transmission of your very massive robot, you may improve your behavior if you're modeling joint elasticity and if you're designing a controller which is based on this model. So for instance, this is just a static reaction of a conventional industrial robot for this KUKA arm, and you see that there are a lot of vibration, while if you do feedback linearization plus high damping in the linear side of the control design, you achieve very better performance. But even while tracking trajectory, on top you see the conventional KUKA controller in 2007, I must add this, and below the one that Michael Tuma developed in his PhD thesis. And you can see that this typical benchmark motion around squares shows negligible vibration for the case of feedback linearization. Okay, what about regulation task? So regulation task is simpler because we don't want to follow trajectory, just position the arm in certain configuration. So we can use also partial feedback measurement, in particular only on the motor side. So we have a PD controller on the motor variable, and in the presence of gravity, we have different ways of compensating gravity. Now, compensating gravity can be done with a pure feed forward, and here I have a list of things. So compensating gravity at the destination from the beginning, or using only motor variable in different ways. And every step requires some condition for guaranteeing global asymptotic stability of the close to equilibrium. In fact, the last step, which is the less requiring one, only requires that the positional gain is positive definite and the stiffness is positive, without any lower bound. And so this is achieved by a special technique which realizes extra gravity cancellation. And I would like to show how this works. So let's start with a trivial example. So a rigid robot under gravity. And we would like to let this robot behave as if gravity was not there. This is very simple because the gravity term G of Q is collocated with the torque. So if we design the torque with a gravity cancellation plus a new torque, we are able to mimic the behavior of our arm, which moves now on a horizontal plane. Then it's a trivial trick. But what about the presence of joint elasticity? In this case, the torque acts on the motor side theta, and then the motor, to the elasticity of the transmission, acts on the position of the Q. So we have a non-collocation between the term that we like to cancel, G of Q, and the input torque. They live into different equations. So how can you do this? In fact, you can do this by using the feedback equivalence concept. So this is the expression of the control law. You see that you don't need only G of Q, you need also the first derivative and the second derivative of the gravity term, which is not really very difficult to obtain, plus the stiffness and the damping and the motor inertia B. Indeed, if K goes to infinity, the second and third term disappear and you recover the rigid phase. In addition, you need also to change transformation and to change coordinate in order to show what happens in the equivalent gravity-free case. Now, this is a principle which is general, the one that I want to illustrate. Let's say, suppose that you have a nonlinear system, and this system is gravity loaded, like in our case for the elastic joint. But you know that this, through feedback transformation and change of coordinate, which are invertible, can be transformed into a linear controllable system. This is what happens with feedback linearization, with the computed torque for the rigid case, or with the extended feedback linearization for the joint elastic case. On the other side, these C are usually called the linearizing out, in our case, with Q variables. On the other hand, you have a gravity-free system, which is exactly like your gravity loaded, but without gravity. So you're not canceling things. You would like just to cancel one particular dynamic effect that annoys you, okay? And indeed, this system, through a different controller and a different change of coordinate, is equivalent to the same linear controllable system, because gravity plays no role in this. So you can just pass from one to the other without simplifying things, in fact, not canceling anything which is related to inertia, coordinates, and sense of real term, which makes a lot of sense and also simplification. I will skip this result. Now, another application of this concept is for vibration damping. Now, you see here a video where when vibration damping is off for the lightweight robot or the KUKA DL3, you have vibration there, but you can achieve vibration damping at the Cartesian level using suitable joint torque sensing and control design. However, if you try to do this with a system that have a large joint elasticity, so lower stiffness than the harmonic drive that the lightweight robot of KUKA is using, then this type of controller does not work. You need something more. You need something more to add damping on the link side of the problem. And this is, in fact, has been done, and it has been done by VLR group. So the problem is as follows. Look at just at the picture, the equation will follow. On one side, you have the conventional joint elastic. On the bottom part, you have added damping on the link side of the problem. So you would like to have an equivalence between these two systems, without canceling whatever else, which would happen if you're using feedback linearization. So in fact, you can find this type of control, and you can find this type of state transformation. And they call this method in 2018 elastic structure preserving control, but in fact, it's the same principle of the equivalence of the previous result for gravity cancellation, which dates back 2010. And this is what happened. This is the system without damping on the link side. This is a variable stiffness actuation. While when you're implementing this damping injection on the link side, you have very smooth and very unvibratory behavior. The last example that I would like to show is a very new one. Suppose that you have, it's a matching of an impedance model for a system that has a joint elasticity. So again, we start with this. What is new is that we have also environment force. As you know, in impedance control, you're not trying to track a trajectory or to control force, but you're trying to match a desired second order model, which relates position error with respect to a given reference trajectory with the environment forces. So here you have the same thing. The only thing is that you have a double the number of equations. So how do you deal with this? If you try to apply say feedback linearization, this is not the case because the system is already linear. But if you try to apply the same concept of non-minimum of no zero in your transfer function, then you will end up with the need of having a measure of the environment force of its first derivative and of its second derivative, which is a mess. So it's impossible to be done. However, if you apply this idea of matching through feedback equivalence system, which has a different characteristic in terms of masses and stiffness and possibly damping, without the other cancellation, and if you make a special assumption for this case, that you don't change the mass on the link side, you're able to change anything else, then there's a feedback control law and a state transformation that and then you can modify your fourth order scheme, so your elastic joint system, into the one that you desire for also a generalized impedance control. Okay, I will skip this. Unfortunately, I'm too late. So I will move to the second part, which is dynamic modeling of flexible arm. Now I start the reverse. I'm starting first with a single link case, which can be approximated by linear dynamics. And you will recognize that many things that have been said this morning are very similar to this case. So we have
sorry to interrupt, but I think it's a good moment to let you know that it's 5 minutes.
Okay. Okay. So just let me say, you can see it's a flexible link that we model as a Euler-Bernoulli beam. There are various functions that you can define. You can see the pure bending in the motion plane. This plane is horizontal, typically. In general, it could be also under gravity. And you can find a PD equation with geometric and dynamic boundary condition, and the equation looks like that. Okay, you can solve this. Well, let me speak how to solve this. But at the end, surprisingly, the model is extremely simple. Once you have set up the correct boundary condition and use the correct variable. So you can see that rigid rotation plus superposed a number of vibration, and you can have a finite dimensional model by considering a finite number of modes. You can include modal damping. You can have two types of output here, and this is what I wanted to stress. The rest you can forget. Again, you can control in this flexible link the position at the base, which is the one that you measure by the encoder and the motor, and you have a minimum phase output. Whereas if you control at the tip level, you have no minimum phase output. Now, what is the result of this? Let me jump to the conclusion. Is that you cannot apply inversion techniques or canceling techniques when you want to track a trajectory at the end effector level. The result is that you end up with instability in the closed loop, and there's nothing you can do unless you resort to very special techniques which require a non-causal solution to the problem of inversion, and or a different way of approaching things like with nonlinear regulation. I think that I will skip all this aspect. Well, let me say just if you move to multiple flexible links, you have a situation which is very similar. You can see that in this case, the inertia matrix is completely full. It depends in general both on the rigid variable theta and on the deformation variable delta. You may include gravity effect, Cauchy sensitivity term. You have a special part, which is the last one, with K delta and plus D delta dot, which is the stiffness of the various modes and their damping. And again, you see that torque is only present on the rigid motion, not on the flexible motion. And in this sense, this structure are, like the previous ones, are also considered as underactuated. And this is a very important aspect. Now, let me say just what are the problems and without giving the solution. So you can have still regulation, and regulation is simple. Like in the joint elastic case, you can do a joint PD plus gravity compensation. You can track joint trajectory by inversion because the input-output map is minimum phase, so you don't introduce instability in the closed loop. You can, if you want to track end effector trajectory, and this is the difficult case, you have to resort either to non-causal solution or to a solution that avoids critical cancellation. And you have also other problems you can consider here. Let me jump completely this part. I'm sorry, there are many results. Okay, let me conclude with a simple application of this concept. So I'm considering one particular model of a soft manipulator, a continuum one, the one introduced by Cosimo. You may be familiar with that. Now, the main point here is that you may have a system which is fully activated. So each segment of this piecewise constant curvature model has an individual activity. And then in this case, you can do whatever you wish, I would say, by mimicking what has been done for the robot, with the only difference that you preserve the stiffness and damping of the natural system. On the other hand, you may be underactuated. So some of this segment may not have a command. by construction or by fault of the actuators. This is another thing that should be considered. So what happened in that case? So if you are actuated, the model looks like this, and you can do a number of things like Cosmo has shown in this paper. If you're under actuated, you can partition the system into actuated coordinates and passive coordinate or unactuated. Sorry, this P should be a U, unactuated coordinate. And you can reorganize things so that you can partition the dynamic model in this way. And if you look to this in this way, it's very similar to the flexible link case as we have seen before. Now you have only a subset of coordinates that are actuated, and you can address a number of problems. I will. So this is what. Okay, in the underactuated case, the first thing you have to question if what is the zero dynamics associated to the output. So you want to control the actuated variable indeed, and you have the unactuated variable that follows dynamically what you're doing on that. You like that they follow without exploding. So the first things that we proved is that in the absence of gravity, there's a unique equilibrium state for the unactuated variable, which is globally asymptotically stable when you fix the output. So when the output is zero, also this variable is zero. In the presence of gravity, indeed, there's a deformation of the unactuated segments, but they converge to a solution, one solution, I would say, not the unique solution in general, of this equation, which connects the stiffness of the unactuated segments with the gravity affecting on the segment. You can see that, indeed, if the gravity is not there, the only solution is Q equals 0, which is the case of absence of gravity. And you can prove this by Lyapunov and Lyapunov. So this gives hope to regulation problem, to realize regulation problem. For instance, if you want to regulate to a desired actuated variable and 0 curvature for in the absence of gravity, then a controller which is only designed on the actuated part with a feed-forward term on the desired curvature of the actuated segment works and works globally. Okay, in the presence of gravity, you can add gravity compensation at the destination, and indeed you need to compute also the desired value of the unactuated variable, which is the unique solution if Kp is sufficiently large and if the stiffness of the unactuated parts is not too low. I would say so. There's a structural condition. So this is unique, and this controller brings you to the desired destination. You can also have a slight variation where you use the current measurement of the unactuated variable, if you have it, okay, and have a better gravity compensation than just with a constant feed-forward term. And this is what happens with this particular case. Here we have 3 segments, 2 are actuated. The first and the third segment are actuated. The second segment has no command. And you can see that you can go from an initial configuration in the presence of gravity to a desired one only for the actuated one, and this is the final result. So the system is bent because the second part is not actuated. But you can use also other controller, for instance, a partial feedback normalization control, which uses the dynamics in order to track trajectory for the actuated part, and the unactuated part remains stable. And so this is because the zero dynamics has been proven to be in this way. Okay, so take-home message, and I conclude with this. I'm sorry for being late, but so first of all, I would say that nowadays, this workshop is one significant example. There's a soft explosion that is now going back to the old results of a mature field of flexible robot control that shows that probably consideration of dynamics is worth, at least for designing a controller if you want to increase performance. There are other things that I even mentioned, which combine feed-forward and feedback in order to achieve robustness with respect to external disturbance. And the feed-forward part may be learned over iteration. For flexible manipulators, there are techniques that learn very efficiently the command without knowing exactly the model. And this is something that can be applied, I'm sure, also for the software application, plus other open problems that are left for fun. And the other take-home message is that what is this feedback equivalence concept? It's not the atom of space, it's not passivity, it's not purely geometric approach, but just simply said that you would like to keep the natural dynamics that is worth keeping. If you design a flexible arm, a continuous soft manipulator, you don't want to stiffen this, as is the traditional way of dealing. But you would like to remove from the picture what is boring you, what is affecting your performance, and keeping all the rest untouched. And this is also simplify the problem from an implementation point of view. And in this way, you don't give up the performance that you have with except cancellation of non-linear terms. And last but not least, indeed, many of these ideas, this is just a scratch of the surface that has been developed over time, adaptive control and so on, for the flexible case or flexible joint or flexible links. I'm sure that they will find application also in the concept of soft manipulator, provided that you take care of the constraint and limitation of the design, so some structural properties, and of course the application of many. Okay, I think I'm done. Thank you for listening, and I'm ready to accept questions.
Yeah, thanks for the amazing talk. I already see two people asking. So first, Stefano would like to ask a question. Please go.
Thank you very much, Alessandro, for the very nice talk. Please correct me if on this state, because basically, I mean, I would definitely agree. So it's always, the standard control is, stiffening things and trying to go against the physics is something you should not do. We definitely agree with that. But correct me if I'm wrong, because basically what you're saying is don't use things which are not collocated. That's the first thing, because you need collocation to be sure that things do not explode. Control, well, of course you can measure the end effector, but basically you're saying, if the system is controllable, which means you have a model that you know where, the base where your control should be to get what you want to have, basically go there and take care that all the energy which is over is damped out, so that eventually the system will get to the end effector. You have predicted a model-based kind of reasoning, but then in a collocated way, which is what I called controlled by interconnection via the port of where the actuator is.
So Stefano, this is embarrassing. I'm pretty sure that you can reformulate this into a Port-Hamiltonian set, to be honest. But,
no, but without talking about Port-Hamiltonian.
But the only thing is that it is true that if you're collocated, there are no problems. But in fact, if you look at this simple example, cancel gravity beyond elasticity, or introducing damping beyond the elasticity, like the DLR ESP method, they are doing something which is non-collocated. Okay. But I'm familiar with the DLR group, and they said that they tried feedback linearization and they never succeed to realize.
No, but that's not what I'm saying. So what I'm saying is, suppose that you have elastic joints and you want to gravity compensate. It means that suppose that you have the old model that you could calculate basically what the configuration would be of your joints in order to reach.
Sure. This is a prerequisite that you
yes, exactly.
In fact, this computation can be made iteratively by layer.
Exactly.
Okay.
Exactly.
So there are. This is one thing. So you have to do. But then the stabilization in that case is collocated. So for regulation only is collocated. What was shown there is that all these methods are approximate. They are exact at steady state. But indeed, even in the rigid case, you have two types of PD control for regulation with gravity handling. One is gravity cancellation. So you remove gravity from the picture. So it's what I wanted to achieve in this case. And the other is you add the right gravity at the destination, but apply this constant torque from the beginning. Okay. Now, indeed, at steady state, they perform the same, but the transit is much different. And the transit is not better when you're canceling things. So the idea of this equivalence, and this is why I put a table with the historical results that step by step went to the final result, is that we are able to remove completely the gravity from the picture, at least at the level of the link side. The motor indeed will be affected. The motor should still compress the joint to sustain gravity. Okay, so the motor will not behave as in the gravity-free case. They will behave different, but in such a way that the link behave as in the gravity-free case. And link are not collocated with the computer. So again, this is my way of interpreting things, but I'm sure, I mean, if I come and visit you in 20,
please.
I
would like to have
I think we can
discussion.
work out this in a nice way.
Thank you.
Okay, we have already no more time, but maybe we can very quickly ask a couple of there are a couple of questions. So Kirill from the audience, maybe you can unmute yourself and answer your question. Okay. Okay, so then Franco, you have the word for the very last question.
Okay. First of all, thank you very much for the talk. It was very insightful, as usual. And my question is actually more a curiosity. When you were speaking about your feedback matching technique, so if I'm not wrong, you say that you can modify the system with the model with a reference model, right?
Yeah.
So the question is, how do you choose the model, the reference model?
Very good. So we are working on that. And there are, let's say, two optimization problems. One is choosing the parameter of your model that you would like to match in such a way that you have the best performance in terms of what you desire. For instance, no overshooting or very quick transfer motion and things like that, or minimizing energy needed to do some displacement. Okay. Once you have done this, and this is a parametric optimization, so you have integral objective function, but you have to modify a number of parameters in order to find the optimum. Okay, and this is one side. Suppose that you have found the right model for the specific application or for the specific segment of your application. And now I give you a torque that maps exactly your original model with the desired one, with the best one. Indeed, the original model may be very different from the optimal one. So you again may formulate an optimal problem which minimizes the effort of matching the model at the price of some error. Okay, and this is another optimal control problem. We are working on both of them. So I have no answer. And for the second order system, so for the impedance of the rigid case, we know everything about linear second order system. We know damping coefficient, we know natural frequency, well, whatever, in closed form. We don't have such a solution for a fourth order system. And this is why we're doing
so for the moment, there are no papers.
No.
There are no published results. Okay.
No. Even that slide is just a slide.
Okay, I will wait. Thank you.
Okay, so